to this transition state theory. And this is a theory that we can apply for really kind of probing in more detail the activation controlled reactions. Okay, so I've been talking about both gas phase and liquid phase diffusion limited reactions, like our fastest possible reactions. But what happens if we don't have a fast reaction and we do have this activated complex or this transition state? Okay, and so we can apply this both to liquids and gases. Okay, and we'll see very similar results. And so this is where we really get into the statistical mechanics and the quantum mechanics. So I'm only going to talk about this really briefly. Okay. So here we have, same mechanism we've been looking before, A plus B, and now I'm just calling this some transition state, C double dagger. Okay. And then there's some equilibrium constant here. We'll write that equilibrium constant as big K double dagger. Okay. And if we were to, balance this reaction overall, as we've been doing, this would just appear as a second order reaction. A plus B goes to products with rate constant K reaction. And then from the previous lecture, right, that activation controlled rate constant goes as little k times big K. Okay, so basically this was like the Kc times the equilibrium constant. Okay, so that's our activation controlled equilibrium value. And we can actually come up with this using equations in statistical mechanics. And so again, I'm not going to derive those, but I'm just going to present it for you directly. And so let's see here. So the way this goes, so from StatMech, the equilibrium constant of this transition state is equal to the partition functions of all players involved. So that would be QC divided by QA times QB. So much like activity, we can write an equilibrium constant in terms of partition functions as well. Okay, so just like with our equilibrium constant, right, products over reactants, so that's all we've done here. But now instead of saying activity, we're going to use the partition function. And then there's also this minimum energy requirement, E raised, and I'm just going to say to the negative, right, EA divided by RT. And so if you recall, those partition functions go as something like 1 over 1 minus E to the negative energy of vibration divided by KBT, where that energy of vibration, E sub nu, right, is just H times nu, where that nu is the frequency of vibration. Okay. And so when we also put that together all in total and using, well, I think I'm gonna stop there. That's all. I don't want to go into too much more detail on this. But what I do want to point out here, right, is this is our partition function, and what we're interested in is the vibrations. So when we talk about the activities of this equilibrium, what's really going on there is it's the vibrations of these molecules that are able to stabilize or destabilize this transition state. Okay, so let's look at this mechanism, same mechanism, but just in a slightly different nomenclature. Okay, so we'll say A reacts with something that has a bond, okay, BC. And that becomes this stable, unstable intermediate. So I noted that that was by C double dagger, but now this is really some weird complex, right? And it is going to have some type of vibrational population. So it's going to have a partition function. And so now that unstable intermediate can go on to form the new chemical bond, AB, and kick out a C molecule. Okay? Well, what's pretty cool, if we were to zoom way in on that transition state, right? So remember, we're interested in this activation energy. If we were to zoom way in there, we would actually find that we could draw vibrational energy levels at that peak. Okay, something that looks like this, right? We've got our potential energy well. Okay, so this displacement, so that's basically just saying like, the bond A, B, and we recognize here is the ground state. So that bond is going to be vibrating at that ground state, right? It's not stationary. And if we were to bring it up to an excited state to level 1, all right, it's going to be vibrating even more. Okay, and that has the effect of increasing its kinetic energy the more we vibrate this molecule. Okay, well, as is the game here, we know that BC is going to have some potential energy curve, and AB is going to have some potential energy curve. So we can look at this in a rather cool way. So we can make what's called a potential energy surface out of this thing. And now we note here that we've got the my reactant bond coordinate BC, right? And here's that potential energy level where, here is like level 1, for example, the ground state. And then here is my AB potential energy well, okay? Where it's vibrating at some ground state. And there will be some minima, some saddle point that we call, that the molecule has to transition through. So this point right here is given by A, B, C. All right? And so if we were to flip this curve up like so, like a topography map, it looks something like this, okay? We're now on this axis right here. This is my RAB. And I know it's hard to recognize this, but this would be my equilibrium bond distance for RAB, right? So here's that potential energy well, okay? And remember, it's vibrating, so this gives me my my equilibrium bond distance, right? That would be like this value right here. But we really recognize like it's oscillating between some value right there, right? And same with RBC. It's really oscillating like, somewhere on this topography map, okay? So the molecule, travels through some transition state, which is where we get this intermediate, okay? So we can look at these in this kind of dynamic way. So this picture right here assumes no vibrations. And this would be consistent if we literally just had an A plus a B going on to make a C. So no, just single atoms reacting, right? They're going to exist in the minima of that potential energy curve. Travel right through the transition state and on to products. So that's how this diagram works. So this is products and this is reactants, okay? So, but what if we did have some bonds, right? And particularly, what if both things had chemical bonds, right? So what if we had like an A, B reacting with a B, C, something like that, okay? To go on and make a C plus B, B. Something crazy like that, right? Well, we recognize here now my reactant is no longer traveling the minima, it's actually oscillating. So this indicates it's oscillating, it's vibrating, okay? Well, as it turns out, to have a successful reaction, to make it through, it's got to be able to travel through that minima and maintain that same phase of vibration. So that would give us a successful reaction. However, if these molecules approached, so you can see that maybe this is like in some ground state. However, if it approached with excess energy, right? So now you can see it's actually oscillating even higher up these curves, okay? Then it might just get kicked right back out of the transition state and go back down the hill, okay? So that would be like if we're looking at this something, it makes it up here, but then it kicks right back down, okay? So these things have got to be vibrating in concert, if you will, to make it out through the transition state, okay? There's another cool possibility that can happen, and that is, what if, let's say, oops, change color. Why did you guys update this program on me? Okay, yeah, I wanted a bright color. So let's say now instead, this is, we've got a reactant at an elevated vibrational state. So, it's doing something like this, and it is able to successfully make it through the transition state, okay? Well, it could make it through this transition state, and there's this possibility then where it comes out at a lower energy state. So what would happen? What would be that result? Well, this is what we call chemiluminescence. So it would give off light as a result of that reaction, right? So you are very familiar with bioluminescence, okay? This is the mechanism by which that occurs, where reactants are approaching each other at an excited state, and they leave the transition state, releasing all of that excess energy. And in some cases, they can release that excess energy in the form of light, which is pretty cool.